Hello, my name is Jean Kim. I'm assistant professor at Texas A&M University. I'm gonna present OmniSoft-A design tool for softness by examples on behalf of my collaboration with Adobe Research and UCLA AGCI Research. Okay, if we look around the world, there are more and more applications that are 3D printable, partly thanks to the online repository that advanced web designers and experts share a sophisticated 3D objects from medical device to rehabilitation gears to even feminine items. But we all have certain concerns that 3D printing, especially with low-cost FDM 3D printing, we can only 3D print rigid objects. But even with such material limitations that is given by the plastics, there are the ways to address these issues with the expected mechanical behaviors, so-called metamaterials. All these are 3D printable shoes, but with different purpose and so provides different comfort when it is worn. Metamaterial is a very common technique. The metamaterial composition is not only found in 3D printing domain, it is actually a very common fabrication method to overcome limited materiality, mainly targeting at random deformations. However, a designer is expected to exactly know how these should be structured to behave in the way that they want the material to deform in certain conditions. And thus, designers are expected to place small microstructures nearby to plan these properties ahead of time. However, many of current computer-aided design systems, the CAD tools in fabrication domain, have focused on the optimization of the 3D object geometry features, so-called the shape features. For end users, parametric user interface with the graphical representations of the shape has championed as the most promising way of manipulating the 3D objects. Parametric UI is great for designing shapes, as I said, but setting constraints of them, such as setting the deformations or setting the properties, is not great, and the simulation does not propose how the end users can do these in the easier way. This is one kind of parametric UI if we design the parametric UI for the soft objects, so the users can adjust the non-visual features with some parameters. Thinking about the properties such as softness, which is the internal characteristics of the objects, they are not interpretable by these values we call as parameters. How would you design the soft buttons with flexible materials? How the softness level 3 means to the user? How the softness 9 means to the user from different user with different intentions. So probably can change this to a little more familiar representation to users using natural language, to the softness from the softest to hardest, or the deformability from easiest to softest. However, again, this is subjective feeling, so there are only limited number of the expression. And also, someone may expect the hardest button for as hard as metal, whereas the other may expect the hardest button as hard enough but pressable with the hard rubbery button and so forth. And actually, also in fact, the information that the fabrication machine, the 3D printer, needs to know to fabricate that substance is different from the user's language. There are a number of factors and parameters that affect the property of the physical 3D objects. This is one screenshot from Cura that we have to set to realize what type of property the softness level can be achieved from different settings. So we noticed that there is a communication gap between the user's expression, which is also hard to express, but also between those user expressions and machine interpretations. Our solution here is suggesting users to remind their previous experiences on existing materials to express them as input. And for machines, optimizing parameters to produce parameters list, such as the right flow rate, right infill densities, and right printing speed, that can be actually used to define the density or the print speed or many other things that actually affects the property, the softness level. For example, you know how soft the dish scrubber is, and you know how stiff your shoe sole or the tire is. So once you specify, oh, this is the right softness that I want in my 3D object, then we can generate the list of the parameters to realize to replicate that exact softness, and the user can specify where they want these softness should be. So, for example, from our user studies, our user placed the soft corner to the end of the furniture and to the top of the guitar so that it doesn't hurt the user play the guitar. There was one case that I wanted to ask if I were live. So how do you think the softness difference could be in these two examples, the makeup sponge and the scrubber? Actually, the answer is exactly the same, but we didn't exclude these as options from the user design tool because then the person who might not familiar with the makeup sponge can still refer to the dish scrubber so that they can use whatever they feel comfortable and familiar as an input object as a reference. So how this can be solved? How can this be addressed? We propose a data-driven approach to interpret the user's expression and obtain characteristics of the object. So using a common device, this is not the device that we use, but we just choose to represent how the substance is measured. So we know how much of force is required to deform the soft objects by pushing them. So we just obtained the common commercial device from Amazon, which is around $20 to $30. So we collected lots of everyday examples, and using the commercial device, we measured the softness and provided this as the softness examples. And by the softness standard number, we tried many 3D printing by differentiating different printing parameters and then see how we can achieve that exact softness by varying these number of 3D printing parameters. So in the inverse function, we can predict what are the best print parameters, and so parameter settings to realize the input softness. That is actually the number, but we can guess from the database specified by number by user, but we can guess from the database once the user choose the real world objects as reference. This is the actual device how we measure the softness, which is called the Softness-A softness scale device. And through the many user studies, we also realized that the way that different users perceive the softness is similar to the standard scale. What does that mean? So once we measure the softness of the object with the softness 5 and measure the softness with 90, then it is obviously the softness 90 is stiffer, and people think that is actually stiffer even from the different perceptions.
From the user study and many examples from our study participants, we learned that designers think that the ability to customize property means actually customizability of functions. Here, one user designed a child-safe furniture so baby doesn't hurt from the sharp corner of the table, and the other proposed ergonomic couch and bike saddle, while the other designs the guitar that does not hurt his thigh when playing. In practice, we can imagine a custom steering wheel that will inform novice drivers the best grip about the driving, and personalized shoe that provides custom comfort while keeping the other global parts rigid, such as heel.
So what can we do? By providing softness as another design factor beyond the shape, we can let the user design a 3D printed facade for the blind users to make the flat home appliances tangible so that they can independently operate those functions. or tactile picture books for younger children so that they can develop the emergent literacy skills through the interactive modalities. They can feel and think and touch from the tangible books. And also we can design subject grippers for the robotics applications and customized grippers and many other examples that we can imagine. We brought Softness as design factor to the early design stage, which was previously detached from the design tool, so was only possible to adjust after completing the design. So we get rid of a tedious iteration processes in case the user feel that the property does not meet in the end. So they adjust the parameters, 3D print, test, and again adjust parameters, 3D print, and test again. Our contribution is threefold. We quantified fabrication factors that affect property of the 3D printed object through many 3D printing parameters. We also identified a relationship between the human's subjective perception and fabricated properties using the standard scales. We also provide a user interface and a list of the library of the common everyday examples with standard scales so that it can be applied to many different material properties or other techniques to create those properties available to the users. I was Jiyun Kim from Texas A&M HCCIED Lab. This work on OmniSoft-A design tool for substance by examples is a collaboration between Texas A&M University Adobe Research and UCLA HCCI Research. Thank you.